All right, so welcome back, everyone. This is part 2 of module 4, where last time we were talking about vectors, and now we're going to talk about matrices. And in general, the purpose of this module, again, is to lay down some framework so that we have the mathematical tools we need to describe quantum systems, and specifically qubits. So you saw yesterday that we could describe the state of a qubit, of a single qubit, as a two-dimensional vector. And after this talk, we're going to talk about, in module 5, how we can modify the state of those qubits using quantum gates. And so a good sketch of what that looks like, just remember that vectors in linear algebra correspond to quantum states, and matrices correspond to quantum gates. So this is all about matrices today. So what's a matrix? A matrix, just like a vector, is just a collection of entries, a collection of numbers of a specific type, and they're organized in a specific way. In this two-dimensional grid you can see here, there are m rows and n columns. M rows and n columns. And so we could say that we have an m by n matrix, an m by n matrix. This matrix has 1, 2, 3, up to m columns. And I'm sorry, m rows and n columns. So yeah, so each entry, we can label each specific entry by aij, and the index I and j refer to the row and column of a matrix respectively. So A11 corresponds to the first row and the first column. AMN corresponds to the very last row and the last column. So this is just a general picture of what matrices looks like. And just a little bit of terminology, which should be pretty straightforward. If all the numbers in the matrix and all the entries of the matrix are real, we're going to call it a real matrix. And if all the entries are complex, we're going to call it a complex matrix. And that should be pretty straightforward. Okay, so let's look at a few examples of matrices. We have a 2 by 3 real matrix here. You can see there are 2 rows and 3 columns, 2 rows and 3 columns. And all of the entries in the matrix are real numbers, and so we call that a real matrix. A special case of a matrix would be what we call a square matrix. And in this case, it's any matrix, 2 by 2, 3 by 3, 4 by 4, etc., where the number of rows is the same as the number of columns. And that's a particularly important kind of matrix, and we'll come back to that a little bit later, what square matrices are. Another special case of a matrix, and you've already seen this, is a vector. A vector is nothing more than a 3 by 1 matrix, sorry, an n by 1 matrix. So if we have a 3-dimensional vector, for instance, this vector here, we could describe this as a 3 by 1 matrix where there are 3 rows, each with 1 element in each row, 1 column. Equivalently, we could describe a row vector using the same notation. This is a 1 by 3 matrix. And again, it has 3 elements. There's only 1 row, and this time 3 columns. And we'll see that the formulation for a matrix and the formulation for a vector are, in fact, the same thing. In linear algebra, we don't have to distinguish between the two things, even though it tends to be a useful distinction. You could easily derive all the properties of matrices from vectors, or vectors from matrices. You can start with either representation. Okay, so what can we do with these matrices? We can add 2 matrices together. And just like with vectors, we can add them together element-wise. So 3, the corresponding elements would be A11, A22, so 3 and 4 are the same element. We add them together to get 7. And you can see it's just a direct map. And as you'd expect, the matrices here have to have the same size. Otherwise, we'd have some issues. It would be impossible to add matrices that didn't have the same size. Okay, pretty straightforward. A scalar multiplication, this is also very similar to scalar multiplication for a vector. If we multiply a matrix by a scalar, it's equivalent to multiplying each element of the matrix by a scalar. So in this case, we have the 2 by 3 matrix, 1, 3, 5, 2, 6, 2, and we multiply 2 by each element, and we get this corresponding matrix. It's the same size, except each of the elements is doubled. Okay, so those properties are properties of a matrix that you should be aware of. We're not going to make particular use of them in quantum computing, at least in the beginning. What we're going to mainly focus on is this operation. What happens when you take a matrix and you multiply it, you multiply it to a vector. You apply it to a vector. And so we can think of this process as a series of inner products, and it's a little bit difficult to visualize this process. And for me, who tends to think very spatially, sometimes you can be thinking about the direction of the multiplication. But there are several different ways to think about how this process works. One is to think of the product of M, the matrix here, which in this case, we're just going to use a really simple 2 by 2 matrix, and the vector V, a very simple two-dimensional vector. And we're going to think of each row as a row vector where we are taking the inner product with the vector in question. So you see we have the first row of the matrix, and we're going to take the inner product of that with the vector. And then we're also going to take the second row of the matrix and take the inner product of that. And we have two inner products. And if you'll remember from yesterday's talk about vectors, when we take the inner product, the results of an inner product is just a single value, a number. And that number for the inner product corresponds to the new value of a new vector, which is the output of this process. So we take a matrix, M, we multiply it by a vector V, or rather we have a vector and we multiply it by a matrix M, and we get a different vector, which is of the same size. In this case, it's of the same size as the original vector, 1739. So this is one way of thinking about how matrix multiplication works. Are there any questions so far about that one? Okay, good. An alternative formulation of how this works is to think of, actually, you know what, before we go on to that, let's do a couple of examples. And then we'll come back to that alternative formulation. So here we are. We have a few simple examples. And these are complex matrices. This is a 2 by 2 complex matrix. And we have a vector here, and we're going to multiply these together. So we can start by breaking this process down into two separate inner products. So we could say that the first inner product is given by this. And the second, and all we're doing here is just breaking up this matrix into two separate rows. And as we saw yesterday, the inner product of two vectors, we take the first element of the first vector times the first element of the second vector, which in this case is I minus I. And we're going to do the same thing with the second inner product, 2 minus I. And we get the following vector, 0, 2 minus I. Does everyone see how we did that? Any questions on that?
Eric,
yes.
Yeah, just simple typo.
Thank you. I have a feeling I was going to make a mistake if I didn't work these out before. Okay, I minus 1. Or let's write it in normal form. -1 plus I. Great. Is everyone no longer confused now that I haven't made a mistake? Okay with that? Have I made another mistake? Okay. Great. So let's take a look at another example. Suppose we have this 3x2 matrix. This is a 3x2 complex matrix, and we're going to multiply it by a two-dimensional vector. So just the same as before, we can break this process up into a series of inner products. 0, -I, I2, 0. Maybe I'll leave it to you all to come up with the vector. We'll just do it. 0 times I is 0, minus 2I. We have I squared, and 0, 2I minus 6. So our resulting vector is -2I, -1, and 2I minus 6. Any questions on that? It's a bit algorithmic, and it's just a process. This is how the procedure works, but there's something we can notice right away. You'll notice that when we take, we start with a 3x2 matrix. The number of columns here, we have 3 columns, and here we have, no, I mean rows. The number of rows. And here we have 2 rows, and this corresponds to the number of elements of our output vector. Good question. You always get a column vector. Why? That's a good question, and it has to do with the input. Well, the way it's formulated, a matrix, we can think of a matrix as a mapping from one vector to another, and that's something we'll get into when we talk about linear transformations later on. But if you start with a column vector, you're going to get some other kind of column vector as an output. All right, another question: should the complex part go before the real part, or vice versa? Yes, if I wrote it incorrectly, normally we would write this as -6 plus 2I. We typically write the real part first, but mathematically speaking, they're the same thing. If you put the first vector first, would you get the same answer? I'm not sure what you mean by putting the first vector first. If you were to take the vector and multiply it by, if you're saying we would swap the direction of these two, swap the vector in the matrix, if that's your question, that's not going to work. And we'll talk a little bit more about why that doesn't work coming up here. But you can't, there's a specific dimension constraint on how this process works, and we'll see that coming up. Okay, so let's go on. Another way to think about matrix multiplication, rather than conceiving of it, yes, Edward, and we'll get to that. Other than conceiving of this as a series of inner products between a row vector and a column vector, we could think of this process, we can think of this process, we can look at the matrix as a series of columns as well. And each of the columns corresponds to a vector, if you will. And again, this is just a bit of a preview. We'll see how this process works a little bit more later on. And we can think of the original elements, the entries of the original vector, as the coefficients that create a linear combination of the vectors in the matrix. So we have 5 times this first column vector that came from the first column of the matrix, and 6 times the second column of the matrix, and you'll notice you get the same answers before. And how this process works is something we'll see coming up, and it's really cool. Okay, so a little exercise for you all. Let's start by applying this process to two-dimensional. We just have an arbitrary two-dimensional 2x2 matrix, and we're going to apply it to these 2 vectors. So what do you get as an output? And you can put your answer in the chat. Okay. Yeah. So we do get the vector AC, and we're going to do this. We're going to do this. I'm going to create a new thing here. Yep, and for the second one, BD, that's correct. So we have A, B, C, D, and 1, 0. So what we're going to do is break this up into 2 inner products. And the reason we're doing it this way is because, well, we'll do it both ways. So we have A and B, and 1 and 0. And then we have C and D, and 1 and 0. And you'll see that these inner products just equal A and C. And similarly, for the second, we do get B and D. And you can see if I were to just switch here these 2 entries, you would select the B value rather than the A value. Good, and so let's think about it the other way. We have the same problem. And we can think about this as the linear combination of the vectors A and C, and B and D. And you'll notice you get the same answer. If you were to swap the 1 and the 0, you would get a different result as well. Great, any questions so far on that? Excellent. Okay, so in general, 2 dimensions is something we're going to be talking about a lot, just because the state for a qubit is a 2-dimensional vector, and so we'll have a lot to do with 2-dimensional vectors in 2-dimensional space. And so if we have a 2x2 matrix, generally speaking, and we apply it to a 2-dimensional vector, we get this as an output. Okay. Another quick exercise, a little more complicated this time. What is this product here? You can put your answer in the chat as well. Yep, 1, -1, 1, -1. That's right. We can go over it quickly. So we have 2, 0. I forgot the problem. On 1. 1, -1. And as inner products, sometimes a short way to think about it would be we start with this inner product, at which point we get 2 times 1 is 2, -1 is 1, And then we could do the same for the other inner products. And it's kind of the same thing. This sort of drawing tends to help. I tend to draw my pencil that way, just so you know what row and column you're talking about. Okay, great. So you'll notice that when we take a matrix and we multiply it by a vector, we get a vector out in return. When we take a matrix and we multiply it by a vector, we get a vector out in return. So we can think of this matrix specifically as performing a transformation on a vector. It can do something to the vector, and different matrices will, a different matrix will have a different effect on the vector. So for two-dimensional vectors, there are a few things we can think about. We could, for instance, reflect a point in the xy plane, which would be described by a two-dimensional vector x and y. We could reflect it about the y-axis. We could reflect it about the x-axis. We could rotate this point 90 degrees, rotate the vector. So what happens? How does a matrix affect the vector? So there are a couple of interesting cases to start with. We have the identity matrix, and the identity matrix exists in all dimensions. It exists in all dimensions, and effectively what it does is it leaves the vector unchanged. If you multiply this vector by this matrix by any vector, you end up with the same vector that you started out with. So that's useful at times, and we'll see when we get to 2-qubit quantum circuits where applying the identity matrix is effectively doing nothing to a particular qubit. So that's useful. We have a reflection matrix. In this case, it's called T, and we apply it. And in this case, you take, this is reflecting across the x-axis. So a y value previously would become the negative of itself. Okay, and then we have a rotation matrix defined by this matrix here. And what this does is it rotates counterclockwise the vector in two-dimensional space. And these are things that in the module, there's some code to play around with how these things work. And we'll leave it to you to, for now, just trust that these work as we say they do. Okay. Food for thought. Can all operations on vectors be described as multiplication by a matrix? If not, what kind of operations can? So you can answer in the chat and give a little explanation to what you're thinking, and we can talk about a few of them. Okay, so we have not all operations. No, because it has to be multidimensional. What do you mean by that, Sahil? It has to be multidimensional. No, because adding two number matrices that sum to primes. Possibly. Well, we can think of, for one example, the inner product. The inner product is an operation on a vector. And the inner product as an operation on a vector doesn't give another vector in return. When we apply the inner product to a vector by, say, another vector or a matrix of one dimension, you get a single number, you get a scalar factor. So that's one example. And so we can think of multiplication by a matrix as a very specific kind of transformation. It's a very specific kind of transformation. What is it? We'll come to it. Right, right. So the kind of transformation is linear, and other transformations on a vector would not be described as linear, and we'll get to that. Okay, so here's the general formulation for any size matrix. We have a matrix and we're going to multiply it by a vector, and you can see that the inner product of the row with the column vector is the entry for each entry of the resulting matrix, resulting vector. Okay, and yeah, so that's what that inner product looks like for the first row and the first column. Okay, so what's the deal with dimensions? We had a question earlier about switching the order of the matrix and the vector around. What's the deal? So let's take a look at a few examples, and we're going to do this not with using any numbers, but just little diagrams. Let's look at a few different examples for how the dimension affects the output of this process. Suppose we start with a 3-dimensional vector and a 3x3 matrix. So a 3x3 matrix. And what we're going to do is apply this matrix multiplication process and just see what the shape of the output is going to look like. So our first inner product is going to be given by this inner product. So we take the first row and the first column, and we get an output. Our second inner product is going to be the second row and the vector, and we get an output. And our third inner product is going to be the third row, third inner product. And so you can see for a 3x3 matrix with a 3-dimensional input vector, we get a 3-dimensional output vector. This is the most common case that we'll deal with in quantum computing, not in particular 3 dimensions, but the idea that we take a vector and we're transforming it into another vector of the same length. 3 elements to start, 3 elements to finish. Another possible process, which we saw in our example earlier, we could take just 2 inner products and we would end up with just a 2-dimensional vector. So you can see in this case we have a 2x3 matrix and a 3-dimensional vector. And what we've done is transform a 3-dimensional vector into a 2-dimensional vector. 3-dimensional vector into a 2-dimensional vector. Equivalently, we could take the opposite. We could take a 3x2 matrix and multiply it by a 2-dimensional vector. And you'll see this time we have 3 inner products that each give a different entry of the matrix, and you end up with a 3-dimensional matrix. So you can see the number of rows in your matrix is going to correspond to the output of the vector. And so let's return to the question of why couldn't we multiply a 1x2 matrix like this? Why would that not work? Well, if we tried to define an inner product between the rows and the columns, we couldn't, because they don't have the same number of elements. Here, our horizontal axis only has 1 element, and the vertical axis has 2, and those dimensions don't match up. The dimensions don't match up. And if they don't match up, we're not able to carry out that process. So we need, what we say is we need the inner dimensions of the matrices to multiply together. So in this case, we have a 3x1 matrix and a 3x3 matrix, and we need these dimensions to be the same for everything to work out. Okay, so that's the process of multiplying matrices, a matrix by a vector. What questions are there so far about this? Let's just pause for a minute and make sure we understand things. Great. Okay then. So let's go ahead and move on and talk about linear transformations. And linear transformations are the crux of this whole thing. We want to talk about what happens when we take a matrix and we apply it to a vector and it modifies into something else. What are the properties? What are the properties of this process? And it turns out there are two specific characteristics of this process. A linear transformation has two specific processes. One is homogeneity, and homogeneity means that if you have a vector and you first multiply it by some scalar quantity, in this case it's the complex number c. If we multiply the complex number c by a vector and then apply some matrix A, it would be the same thing as applying the matrix A directly to the vector V and then multiplying the complex number afterwards. Does everyone see that this is true? Is this something that makes sense to everyone, or maybe we should do an example? Let's do an example. Okay, so why is it true that why is the homogeneity property true? Okay, so let's get blank slate here, clear everything. Okay, so suppose we have the vector 1, 2. We have the matrix 1, 0, 1, 0. You'll notice this is just the identity matrix we talked about earlier. Actually, let's scratch that. Let's do this matrix. And this is another matrix that you'll see come up. This is called forecasting. It's called the X matrix. And what happens if we apply this matrix to this vector? You can see from the inner products that we get a two by one dimensional, two-dimensional vector, 2 and 1. Okay, so that's the output vector. And what happened is we basically switched the elements. So 1, 2 became 2, 1. That's fine. So suppose then that we apply first a constant. Say we wanted to multiply this by 3. This is our number 3. This is C in this case. So instead our problem becomes 3 and 6. Does everyone see 3 times this vector here gives 3 and 6? Okay, and we can get our answer. Our answer is going to be 6, 3. Now, if I took 3 and I multiplied it after the fact to whatever this thing is, I multiplied that retroactively by 3, it'd be the same thing as multiplying that by the answer of this, and that would give me the same vector, 6 and 3. Great, so any questions about what we're calling the homogeneity property? Questions about that? Does that make sense? Great. Okay, so the second property, which is equally, if not more important, it'd be hard to say which one is important because they both matter, but we're going to make use of this additivity property a lot. The idea is if you have an addition of two vectors, which we'll come to see this as a superposition of two vectors. You have an addition. If you apply a linear transformation to the sum of the two vectors, it's the same thing as applying the linear transformation to both individually and then taking the sum. Okay, so this is analogous to the distributive property for multiplication and addition. And so we can show that as well we can say that if we have, let's just say a general matrix A, B, C, and D. This is the example we saw before, and we're going to multiply it by the sum of 1, 0 plus 0, 1. We're going to say that that's the same thing as the matrix multiplied by the vector 1, 1, which in turn will give you the output A plus C and B plus D. And if that's confusing to you, it's confusing to me too, because I've defined the matrix differently than I did in the previous example. So sorry about that. Now let's take a look at what happens if we apply the matrix A, B, C, and D to each vector individually. Apply the vector to the matrix to each vector individually. And we've already sort of computed these outcomes. This is the same thing as saying A and B plus C and D. And you'll notice we get the same answer. So this is what we call the additivity property. Questions on that? These are two very, very important properties of linear transformations, and we'll make use of them a lot when we're extrapolating to quantum states and quantum gates. Okay, so the most important thing that I'll talk about here today in this talk is linear transformations on the standard basis. The idea is that we'll be able to represent a linear transformation by its effect on each of the basis states individually. So we're going to use the three-dimensional case as an example to show how this works, but it works in any dimension, and we'll see how that works. So let me start by saying that if we have a matrix A, we're going to apply it to a vector V, and this is a general vector V where the elements are V1, V2, and V3. And what I can do is I can rewrite this vector V1, V2, and V3 as a linear combination of the basis states. And this is something we went through yesterday, the standard basis, 1, 0, 0, 0, 1, 0, 0, 0, 1. These vectors represent the standard basis. And I can represent this general vector in terms of the standard basis, these building blocks, if you will. So now that I've rewritten this vector, I can use the homogeneity property to say that it's rather the additivity property, that I can apply this matrix A to each of these elements of the sum individually. Each of these elements of the sum individually. So now that I've done that, I can use the homogeneity property to rewrite these products, A times V1 times this vector, as the effect of A on the basis state, the effect of A on the basis state, the effect of A on the basis state. So what ends up happening is each element of the vector is just what happens when you apply the matrix A to each of the basis states. And then we can use those results as building blocks for our final vector. So this becomes a new basis, if you will. A times the basis vector becomes the new way that we build our output vector based on these coefficients V1, V2, and V3. And if this sort of thing looks familiar, we take the elements of our input vector and we're using them as coefficients in a linear combination of vectors. That's because we've seen it before. We talked about it just earlier in the two-dimensional case, and we're using each entry as a linear combination of the basis vectors. Okay, so what does this look like? The effect of a general matrix A on the basis state. You can notice that for any matrix A, this is just a general matrix. I haven't made any assumptions about what this matrix is. It just has elements A00 through A22, and they're all listed here. For any matrix A, the effect on the standard basis is that we take the first, second, and third columns, respectively, for each basis state. So the first basis state, we take the first column of the matrix. If we apply A to the second basis state, we get the second column of the matrix. And if we apply A to the third basis state, we get the third column of the matrix. And so what we can do is we can use this property to build linear transformations based on how they affect the basis state. So let's look at an example. Suppose that we have a four-dimensional standard basis. We have a four-dimensional standard basis, and it looks like this. And I've gone ahead and labeled this basis using ket notation, and if that throws you, we can just focus on the vectors. But it's easier, rather than to write the vector a million times, I can just label it by this. And you'll see that this is a pretty useful notation in quantum computing, so it'll be useful to get used to it. So we have this basis in 4 dimensions, and we want to apply a general matrix A. In this case, A is a 4x4 matrix, and we want to apply that to the basis states. And suppose when we do that, we get these 4 vectors. How would we build a linear transformation? What would the linear transformation, the matrix, look like such that when you apply it to the 0 basis state, you get this vector. When you apply it to the 1 basis state, you get this vector, etc. So you can type your thoughts into the chat. Let me know what you think. Okay, there we go. So we've got the idea. That's right. So the idea is that we're going to basically compile these individual vectors into one vector, into one matrix. So what does that look like? Let's see here, I've written out the problem. The final matrix, as you've all mentioned, is 1, -2, 3, 6. And that comes from the first vector here, second vector, -2, 5, 12, 4, -3, 9, 1, 7, 8, 1, 2, 6. And I can build a matrix based on its effect on the standard basis elements. And so just as a preview, we'll want to be able to decide how do we want our gate to affect the 0 state, and how do we want our gate to affect the 1 state, etc. So we've got a question here. A 0 would be the first column, a 1 would be, okay, no, that was an answer. Great. So let's move on. This is the last thing we're going to talk about. Suppose that we have a quantum gate Q, and it's going to act on the 2-dimensional general qubit state psi equals alpha times the first basis state, 0, plus beta times the second basis state. We can say that Q acts on each basis state independently. And so the effect of Q on the state is going to be the effect of Q on the individual basis states independently. And so that's the idea. That's how these ideas are going to get used in quantum mechanics. And yeah, last thing to think about, and I'm going to kick the results of this question down to Andrea, who's going to finish module 5 with you today. But let's talk a little bit about what the constraints should be on these linear transformations. What can they do and can't they do? And you feel free to talk about some ideas here. We know that for a qubit state, the vector, our state vector given by alpha and beta, 2-dimensional state vector, has this constraint. So what would that mean about the linear transformation? What could it do and could it not do? I'll invite you to think as a start about this dimension property. We had a 3 by 3 matrix applied to a 3-dimensional vector, gives us a three-dimensional output vector. And here we had a 3-dimensional output vector converted to a 2-dimensional vector. So what kind of constraints do we have on these linear transformations such that they will work in our description of quantum systems? Because there's a lot of math out there. It doesn't necessarily have to apply to quantum systems, and there are a lot of things we can do with matrices that have nothing to do with quantum. But there are certain types of matrices that have everything to do with quantum. So what's the deal? It must obey the quadratic equation. So the quadratic equation, in my understanding, has to do with scalar quantities. And I don't think that's relevant to the situation. Yeah, I'm not sure I understand. For instance, suppose we have a quantum system that's described by a 4-dimensional vector. And we have v1, v2, v3, and v4. Would it make sense physically if we were to map this vector to a 2-dimensional vector? Would that make sense? Yeah. So for starters, Miles has it, yes, we want the output vector to be the same dimension as the input vector. In this case, that's an additional constraint. That's not necessarily the case for all matrix multiplication, but it will be the case for quantum computing. And so what's going to happen is we're going to be looking exclusively when it comes to gates at square matrices. Matrices that take the dimension of the input vector, which is given by the number of columns, and map it to the dimension of the output vector, which should be the same. So we have, we'll have 2 by 2 matrices, 4 by 4 matrices, etc. And this Born's rule, this probability constraint is something that Andrea will talk to you about in the next talk. All right, so any other questions before we move on?